So I'll be talking today about how artificial neural networks begin to learn. I put artificial as well in the title to make it clear. So some background and motivation. Let me first very briefly describe what are artificial neural networks. So there are models that are loosely inspired by the way brain works. They are composed of layers. Each layer is composed of neurons, and they transform input into desired output. So for instance, we could design a neural network which transfers an image into two neurons. One of them will tell us whether it's a dog, and the other will tell us whether it's a cat. In this case, it says with 62% probability that it's a dog, and that's obviously incorrect. Which brings me to the second thing which I have to describe, which is how we train these models. So we pass them a lot of examples of input and the correct output, and we, by an iterative procedure, try to nudge or move the weights that define the connections, so that the next time the neural network gives us an output which is closer to what we want. So artificial neural networks, unfortunately, are, it dropped. 1 second, sorry. Okay, now it's better. Okay, so artificial neural networks are unfortunately a black box. So we don't really understand what's going on. For instance, we don't know how the neural network will react to an image which is perturbed in some way. So for instance, it has a different brightness level. We also don't know how many samples we really need to get them to work robustly. Well, that's fine if we are predicting images of cats and dogs. It's far from being okay if we are working on, let's say, predicting breast cancer in medical images and other critical applications. We really need to understand them if we want to apply them and make authorities accept them. So let me describe briefly how people approach analyzing neural networks typically. So imagine training neural network as a trajectory which goes from some initial point to some final point. So you can think about this trajectory as like going from childhood to adulthood of this model. And what people typically do is they look at this final model and they ponder. So they will ask questions like, well, it has a lot of neurons, so probably needs a lot of data. Or for instance, it has this specific architecture which seems to mimic the way in brain processes images, so probably it will be, let's say, sample efficient on images. Well, it's very useful. In this talk, I will advocate for a slightly different approach, which is to look at this whole training trajectory. So to use a loose analogy, when analyzing person's behavior, we would like to revisit its childhood. And that's sort of the approach that I'm advocating for. So to advocate for it, I will describe an example investigation. So we'll try to understand how artificial neural networks begin to learn as an example of how this can help us understand neural networks. So this comes from, so to start with, this comes from Achilles and Salato paper. So they claim that in artificial neural networks, a similar phenomena which happens in the real brain called critical periods of learning happens. So critical period of learning, as far as I understand, is a phenomena that if we do not acquire a given task, a given skill in the beginning, in a certain phase called the critical period, it will be very difficult to acquire it later. As an example experiment, you could put an eye patch on one of the eyes of a kitten and then remove it, let's say, after 100 days, and it can be shown that this cat will never fully recover stereo vision. And that's actually one of the reasons it's very important that newborns do not have any problems with their eyesight, because it can carry over towards their adulthood, right? So how can we show a similar phenomena happening in artificial neural networks? Sorry, I have to adjust again. Okay, I don't know. So, as I said, we trained the neural networks by repeatedly showing them examples. Each time we pass through all of the examples, we call an epoch. So what the authors do is they pass for the first n epochs, as visible at the top of this figure. They pass blurred versions of the image. And then for 160 epochs, they will pass normal images. This is a famous data set called CIFA-10. After this procedure, they will test performance of the neural network on unseen data And that's given on the y-axis on the left-hand side. So and on the x-axis, we have how many epochs in the beginning we have applied the deficit. As you can see, if we do not apply deficit at all, we have 94% test accuracy. And that's pretty good on this data set. But what happens is that as we go to the right, as we apply more and as we train on longer and longer phase with blurred images, the test set performance degrades rapidly. It goes to like 90% like after 60 epochs of seeing these blurred images, and to like 82, which is a drastic reduction in performance if the blurred images were applied in 140 epochs. Now on the right-hand side, we see that qualitatively a similar phenomena happens in kittens. So this is this experiment, which might be considered a bit immoral, where we put an eye patch on one of the eyes of the kitten, and we remove it after k days, where like it's on the x-axis. On y-axis, we have some sort of measurement of how good or bad is the vision, and qualitatively it follows the same dynamic. So we have established a phenomenon that happens. Let's try to understand why it happens, and I will give two investigations. One comes from our paper, but the figures are actually from not ours follow-up. So there are things that happen in the early phase which carry over into the adulthood of the artificial neural network. One of the things is that even though we pass these examples over and over in a randomized order, there is a subset of examples that the neural network gets very right very soon. So the experiment runs as follows. We can train for one epoch, meaning that we only see each example once, which is actually very few times. So we see each example only once. And we repeat this experiment many times. And we set aside the subset of examples that are correctly classified correctly by the neural network after this short period of training. And that's plotted on the left side of this figure. On the right side, we'll have the examples that are difficult. And the neural network needs more epochs to get them right. Now we subset into classes of, into airplanes, so they are comparable. And I hope you can see the airplanes that are easy for the network are literally just blue backgrounds. So the neural network in the beginning learns to classify correctly these images by just paying attention to the background. So there are many promises that like artificial neural networks are super intelligent, but that's kind of dumb, in my opinion. The problem, as I will try to argue later, is that this doesn't really change. And the neural network still makes these decisions based on the background, even in the end of the training. Now, the difficult types of examples are clearly more difficult, and in particular, they all have a different background. None of these difficult airplanes have blue background. As the second and last investigation I want to present, it comes from an aptly titled paper, Opening the Black Box of Deep Neural Networks. So another thing that happens in this early phase of training is that even though we train all the weights and all the layers simultaneously, it turns out that the early layers, meaning the layers closer to the input, converge to the final solution almost immediately, very, very quickly. And the problem probably is, and that's in the hypothesis space, that this decision to converge these layers is never revisited. So in the context of the experiment with blurred images, we pass blurred images. That's when we learn the early layers, and they are into their final representation, or they have their final connection set, and we never revisit this decision. And I'm pretty sure a similar argument is often made in neuroscience, within the context of like limited neuroplasticity. So there is this connection as well. So here's how we can read this from this plot. And this is the most difficult plot to read in this talk, but also the last one. So as I said, we train neural networks in this way that we nudged or moved weights in some direction that the next time is better. So we need these directions. They are computed using gradients. And for every layer, given here by color, we'll have direction in which we should go and magnitude, like how far we should go. Oh, that's mine? Oh, sorry. Okay. So yeah. This magnitude is given in color and solid line, and the x-axis is epoch. So you can see that this magnitude goes down very rapidly, and this makes sense because as we approach the final solution, we don't move much. Now, this direction has some noise, meaning that we are not sure where to really go. And this is given a dashed line. And the dashed line for every layer goes up, which also makes sense because as we converge to final solution, we are less and less sure where to go to improve the network. Now, the interesting part is that the crossover point, when the noise is larger than the magnitude, and that's like, to use an analogy, that would be like a radio on which the static noise has larger volume than the noise of the presenter, is happening for the red layer, which is the early one, like around epoch 100, and for the last one, around epoch 1000. So they converge really sequentially. And most of the training is with the red layer converged. So this is everything I wanted to talk about. So to summarize, analyzing the training trajectory is an emerging approach towards understanding deep networks. Perhaps it will help us answer all of these difficult questions we have. And the early phase of training is, and especially the early phase of training is critical, this childhood of this model. And to summarize 2 investigations that I have presented, by learning to classify simple examples, these airplanes on blue background, we solidify and find final ways of the early layers. So thank you for your attention.